Welcome back to my favorite people, and thank you very much for watching this lecture video. In last lecture, I went through Fiedel-Crafts alkylation, and I showed you some of the limitation with this reaction. And we said that we have rearrangement, and in order to avoid the rearrangement, we can use oscillation. In oscillation, we will have a carbonyl group attached to the ring. Now, how do we get the carbonyl group? We have to reduce it. And we reduce that carbonyl group, it will turn to water, and the rest we will have a saturated molecule. And we said any electron with a group, any electron withdrawing group on the ring will technically shut down the reaction. So we cannot have any group that is capable of pulling electron density of from the ring. For example, if you run this reaction, the oscillation, and you get this product is going to have a carbonyl group attached to the ring. And the carbonyl group is electron withdrawing group. So that carbonyl group is going to pull electron density from the ring. Is it possible to get another acyl group attached to the ring? And my answer is going to be no. In this case, we're not gonna have two technically an acyl group attached to the ring, and the reaction is gonna stop there. Okay, now in this lecture, I'm gonna spend time to show you how to reduce carbonyl group as a product of like a oscillation reaction, and you have to keep this one in your mind that sometimes your compound, it has maybe it has a lone pair, so it will be sensitive to acidic condition, or like it will be sensitive to acidic condition. And if you use the acidic condition, you might break the reaction, the compound. And so then you have to choose you have to choose a specific condition to reduce that technically carbonyl group. I'm going to start with the Mazingo reaction. The Mazingo reaction, you can run the reaction under neutral condition. And in this case, we have two thiol groups. And this one, it will be added to the ring. Well, sorry, it will be added to the carbonyl group, and we will get such a thing. Okay, so we will have carbon there, and then two sulfurs. Okay. Those two sulfur, they will give up their H's, and they will attach to the ring. So maybe I need to move this one a bit from my back. Move it a bit away. Then I have sulfur here. Now let's connect them to the carbon. Okay. Now I got this plus. Okay, what happened with oxygen? Oxygen is going to take these two hydrogens, and they will be paired with oxygen, and it will leave the system as H2O. Next step, we're going to reduce those hydrogens. So we will use hydrogen gas and nickel. And what do we get? Instead of two sulfur, those two technically bonds, they will be reduced, and we will have two hydrogens. So two hydrogens will show up here. Now this carbon, it will have sp3 hybridization and completely saturated. Okay, completely saturated. So from carbonyl, I turn it to a saturated compound. Now what happened with the sulfurs? The sulfur, we will get 2 mole of nickel sulfur, and also keep this one in your mind that you do have two carbons there. What will happen to those two carbons? They will show up as CH3. So we get ethane gas and as well. So we get water, and we managed to saturate the carbonyl group. We turn it simply we turn it to CH3, or if it's a ketone, it will turn to technically CH2. And then we got 2 mole of nickel sulfide plus ethane gas as well. Okay, can I use this method for just aldehyde, or is capable of being used for ketone as well? And now you can use it actually for both of them, for aldehyde and ketone. And next mechanism, you can use it under a strong basic condition like potassium hydroxide, and simply the carbonyl group it will be the carbonyl group it will leave it will give up the oxygen, and oxygen it will leave the system as H2O. Okay, where do I get those two hydrogen? Those two hydrogen, remember that N2H4 it comes with 4 hydrogen. 2 of them will live with oxygen as water molecule. We need 2 more. Okay, 2 more. Those 2 more they will show up on the carbonyl group. So now I use 4 hydrogen, and I managed to saturate the carbonyl group. Also, I got water. Now I'm left with nitrogen. What will happen to the nitrogen? Nitrogen is going to leave the system as N2 gas. So the carbonyl group got saturated, we got water, and also nitrogen gas. And this method, which is Wolff-Kishner reaction, it can be used under basic condition. And the Clemmensen reduction reaction, the one that I mentioned in the previous lecture, we use it for under acidic condition, and also we apply heat. And in this case, we will get simply the carbonyl group will be saturated, and we will have 2 hydrogens there. Okay, again, so similar to the previous methods, the carbonyl group got saturated, and we got water molecule as well. Okay, the oxygen left as water molecule. I want to spend some time and talk about mechanism of this reaction. Still, there are a good number of questions about it, but one common or acceptable idea is this one that I'm gonna actually write it right now for you. We have acid. What's the purpose of the acid? We have H attached to chloride. Chloride, it has more electronegativity. Now oxygen is gonna go after that hydrogen, and it will grab hydrogen from the acid. Now oxygen still has 1 lone pair, so oxygen now it has a positive charge. And next step, zinc, it will get involved, and zinc it will use 1 of those lone pair or 2 of its electron, and it will attack that carbon. Okay, why that carbon? Because the carbon is attached to oxygen with a positive charge, so carbon has a good amount of like a good amount of positive charge. Okay, now zinc will be attacked. It will be attached to carbon. Okay, and if that one happen, zinc is going to get a positive charge, and here we will have hydrogen attached to oxygen, and oxygen it has 2 lone pair. Now it will be neutral. And again, zinc it has a positive charge, so if there is a species with a negative charge, that's a species I can see zinc. And chloride is going to see zinc, and it will be attached to it. So now we will get this. Okay, zinc with a positive charge is going to get a negative charge from chloride, and it will turn to neutral. And again, here we have oxygen with 2 lone pair and also hydrogen attached to it. And if still you have acidic condition, that OH is capable of actually getting acidic H, because it has 2 lone pair. And if that one happen, now we will get new hydrogen. So we got new hydrogen there, and we have only 1 lone pair in oxygen. This one will have a positive charge. And remember, here we do have zinc that's attached to chloride. Okay, so now OH turned to technically this OH group. Give me that OH group turned to H2O. H2O is a good living group, so now this one it can leave the system, and if this one leave the system, we will have H2O here. So those 2 electrons will be taken by oxygen, and it will leave the system, but it's going to leave a positive charge on carbon. So now we're going to have a positive charge on carbon. And what else? We have zinc, and zinc, it has chloride attached to it. Okay. And so in the next step, okay, because zinc attached to carbon with a positive charge, zinc is going to try to give some electron density to carbon, or carbon is going to try to steal electron from zinc. And if that one happens, zinc is going to be short of electrons, so it will try to pull electron and some electron density from chloride. And we have another zinc, and that zinc is going to come after chloride. Okay, so we're going to pull that chloride. Okay, that zinc is coming with 2 electrons. So we will pull that chloride. Now we will have a zinc with a negative charge, technically. We have a carbon here with a positive charge. Okay, that zinc now it can share the lone pair with carbon. And if that one happens, zinc is going to lose 2 electrons. Okay, zinc is going to lose 2 electrons, and it will make carbon negative. So now carbon is negative. Maybe I should write the negative charge somewhere here. And what will happen to zinc? Zinc lost 2 electrons. If you lose 2 electrons, okay, in that case, the charge from -1, it will turn to +1. So now we have a +1 charge on zinc. Okay, in that case, okay, carbon with a negative charge is going to go after this acidic hydrogen, and it will take that hydrogen from it. So what do we get here? Now we got H there. Okay, we got H attached to carbon. And what else? We have zinc with a positive charge. Zinc with a positive charge attached to carbon. Okay, next step, this chloride, it can donate electron to zinc, and zinc, it can give up those 2 electrons, and it will give them to carbon. Okay, so what do we get here? We get zinc chloride. Okay, zinc chloride is going to leave the system. And here we will have negative charge on carbon. And remember, we do have hydrogen there. Now, this one, it has -1 charge. Again, similar to the previous step, it's going to go after hydrogen, and it will put the new hydrogen. It will pull this new hydrogen from the HCl, and it will turn to a saturated compound. Okay, so as you see, okay, reaction initiated by creating a positive charge on carbon. Okay, how we had to pull the electron density from carbon by introducing, like electrophile like H+. H+ attached to oxygen and managed to create a good positive charge on carbon. Now that we have a positive charge, this one is more capable of getting involved in an addition reaction technically. And yes, the mechanism is a bit complicated, but it's not a bad idea to go through it and learn the mechanism. And this is going to be the end of this lecture, and thank you very much.